Hi, my name is Linda Ortiz. This is my Lab 5 at Home video lab report. The main objective is to observe the motion of falling objects, specifically one object that is dropping rapidly and one that is dropping slowly due to a drag force. For this lab, viscous drag force. The main result is to determine the effect that the viscous drag force has upon an object. Ultimately, it slows down an object as compared with an object only dealing with the force of gravity. My two objects are an apple and a magnolia leaf. The magnolia leaf will turn out to be the object dealing with a viscous drag force. Here I have written down the masses of my objects in kilograms along with their lengths in meters. Here's a clip of my video where I dropped the two objects alongside each other. Within Tracker, I have focused in on frames 45 to 85. Here in Tracker, I am locating my apple on the origin of my cross axis, where the drop will fall along the y-axis. With my calibrator stick, I set the length of my apple to 0.065 meters. With point mass, I pinpoint the apple as it falls throughout the frames, to later observe position relative to time. Now I do the same for the leaf. I apply my leaf to the origin of the cross-axis, so the drop will run along the y-axis. I use my calibrator stick to set the length of the leaf at 0.2 meters. With point mass, I pinpoint the leaf as it falls throughout the frames to later observe its position relative to time. In slow motion, you really get a chance to see what the drag forces have on the leaf. Now I have taken the data from Tracker and moved it to Excel where I could visually observe the graphs showing position relative to time. Already, I can observe how a drag force has affected the drop of the leaf, causing it to drop slower than that of the apple. Here, I put the two graphs on top of each other, and you see the red is leaf, and you can see how long it took for it to actually hit the ground versus the apple. Now before I move on to my computational model, I've calculated the force of gravity solely acting upon both the apple and the leaf. The force of gravity is obtained by multiplying mass by gravity, and the units will be in kilograms meters per second squared, or newtons. On VPython, I have set up my initial velocity at 0, since the objects were at rest before dropping. I have set up my time step to be 0.333 seconds between frames. I made sure to code in how to find the force of gravity within VPython. Since I am observing the apple first, I set the mass accordingly and the time frame it took to hit the ground, which was 0.865 seconds. After I did the apple, I set in everything for the leaf. I changed the mass accordingly to the dimensions of the leaf and the time it took to hit the ground, which was 1.333 seconds. After looking at the animations, I turned the information brought from the CSV files of VPython into Excel. From those graphs that I made, I would be able to see the predicted position relative to time of the apple and the leaf. And here's where exactly you will see where I've extracted data from VPython to graph the predicted position relative to time when knowing the force of gravity is acting upon both objects. Here I've calculated the viscous drag force that is acting upon the objects using the formula of the negative unit vector multiplied by the magnitude and b. Just looking at the calculations, you can see how the drag force is acting greater upon the leaf versus the apple. Here I code the formula for drag force, viscous drag force, into VPython and observe the effects on the objects through the animations. Within VPython, I made sure to write code that would update the system's velocity and the position, so that after I finish, I could take the CSV files, push it into Tracker, create some graphs, and finally observe how the observed droppings of the leaf and the apple compare to the computational model's predicted position relative to time. If everything was done correctly, they should prove quite similar. Here's where I've compared and made connections between models. After several trials, I found B for both the apple and the leaf. From these graphs, you can see how the prediction relates to observed motions of the objects. In conclusion, I found out that the computational model did a pretty well job of coming close to the physical observed model, as you see here with these best fit lines obtained from the formulas of viscous drag force. So now on to what does it mean? The model without drag is predicting a terminal velocity. When observing the velocities as functions of time with VPython, you will see that over the same period of time, it is the model without drag that reaches the greatest velocity, the terminal velocity, compared to that of the model with drag that is slowed down and reaches a lower velocity. Now it's time for what if. After changing the initial velocities of the model with drag and without drag, I have noticed similar observations to the what does it mean. The model without drag still manages to reach a greater velocity, terminal velocity, than the model with drag. The model with drag is slowed down and still fails to reach a greater velocity, even with initial velocity change. Thank you, that is the end of my video lab report.